Assalamualaikum and good day to Doctor and everyone. We are from Group E, the Higgs Hunter. The title of our presentation is Unveiling the Higgs Boson. Before we begin, let me introduce to the team. My name is Christina and I'm joined with my colleague Naimah Husna, Nur Nada Atia and Siti Aisyah. Now, a question like why do some of these particles have mass and others don't? So, it is when the Higgs mechanism plays a key role in our understanding of the universe. The Higgs mechanism is a process in particle physics that explains how particles acquire mass. It is a key part of the standard model and it is associated with the Higgs field and its particle, the Higgs boson. Without the Higgs mechanism, particle will remain massless, making the universe as we know it's impossible. Let's first look at symmetry breaking. So before symmetry breaking, forces in universe are unified. After the Big Bang, the Higgs field transitioned from a uniform state to a specific value, breaking symmetry and enabling particles to gain mass. Symmetry breaking explains why certain particles, such as electron, gain mass while others don't, such as photon, which remain massless. The Higgs field value shifted from uniform to an asymmetric state, creating distinct properties for the particles. Next is mass acquisition. Particles gain mass through interaction with the Higgs field. Stronger interaction results in a great mass, while no interaction leaves particles massless like photons. Some particles, like photons, which is the particle of light, they don't interact with the Higgs field at all, which is why they remain massless and travel at the speed of light. Let's understand about the Higgs field. The Higgs field is an invisible energy field that pervades the entire universe, which in other words, it is like invisible energy that fills the whole universe everywhere all the time. The Higgs field emerged after the Big Bang, creating the condition necessary for the particles to acquire mass. So, how do we know the Higgs field exists? The answer lies on the Higgs boson. The Higgs boson is a particle that represents a quantum of the Higgs field. By looking at this diagram here, the ball shape is the Higgs potential. The orange shape shows the energy of the Higgs field, and the top of the hill represents the symmetric state, which have the high energy, and the valley represents the broken symmetry state, which have a low energy. This diagram explains how particles get their mass. Without the Higgs field, particles would be massless, like bosons. For the next diagram, the white dots in the background represent the Higgs field. This field is spread throughout the entire universe and exists everywhere, even though we can't see it. Particles move through the Higgs field, but not all interact in the same way. The yellow color represents the photons. Photons don't interact with the Higgs field at all. They remain massless and can travel at the speed of light. The red color represents the electron. Electrons interact a little with the Higgs field. This gives them a small mass. And the blue color represents quark. Quark interact strongly with the Higgs field. This gives them a larger mass. The Higgs mechanism explains why particles like electrons and quark have mass. Without it, everything in the universe will behave like light, and matter as we know it couldn't exist.
The next part is the discovery of the Higgs boson. First, the discovery of the Higgs boson in 2012 at the Large Hadron Collider experimental facility provided definitive evidence of both the existence of the Higgs field and the mass generation process via the Higgs mechanism. Due to its high mass and rapid decay, detecting the Higgs boson to prove existence of the associated mass imparting Higgs field posed a tremendous experimental challenge requiring new technological capabilities. Powerful particle accelerators were needed to collide other particles at immense energies to produce the Higgs boson, which then quickly decays into jets of lighter particles that can be detected. It is also involved work at the Large Hadron Collider at CERN, accelerates beams of protons to nearly the speed of light and smash them together 600 million times per second. Sophisticated detectors surround the collision points to analyze the complex particle debris showers and infer what particles were created from the immense energy of each collision by tracking trajectories, energy deposits, and other signatures. It was announced in 2012 after painstaking statistical analysis of the overwhelming background particle production, leaving a new particle consistent of within the Higgs boson. Its definitive mass and other properties such as spin and parity matching theoretical expectations provide strong confirmation that the long sought after linchpin of the mass generation mechanism had finally been found. It was confirmed to be a Higgs boson through extensive analysis of its mass, lifetime, decay modes, quantum spin, and production or decay rates. Several independent decay channels were observed at rates consistent with theoretical models, including decay into two photons, Z bosons, W bosons, tau leptons, and bottom quarks. Next, we will go to the standard model for Higgs boson. In the standard model, the Higgs particle is a massive scalar boson with zero spin, even positive parity, no electric charge, and no color charge that covers to interact with mass. It's also very unstable, decaying into other particles almost immediately upon generation. In the standard model, the particles and force in nature, aside from gravity, arise from properties of quantum fields known as Gauss invariance and symmetries. Forces in the standard model are transmitted by particles known as Gauss forces. The problem was that symmetry requirements for these two forces incorrectly predicted the weak force Gauss bosons W and Z would have zero mass. In specialized terminology of particle physics, mass refers specifically to a particle's rest mass. But experiments show the W and Z Gauss bosons had non-zero rest mass. Further, many promising solutions seem to require the existence of extra particles known as Goldstone bosons. But evidence suggested this did not exist either. This means either Gauss invariance was an incorrect approach or something unknown was giving the weak force W and Z bosons their mass, and doing it in a way that did not create Goldstone bosons. By the late 1950s and early 1960s, physicists were at a loss as to how to resolve these issues or how to create a comprehensive theory of particle physics.
Next, I would like to continue with detection technique. So, to detect Higgs boson, we can use these 5 detection technique. The first technique is high energy particle collision. This is because the Large Hadron Collider (LHC) achieve high energy collision by accelerating protons to nearly the speed of light in a circular track of 27 kilometers long. This collision recreate conditions similar to the early universe, where the Higgs boson is thought to have played a pivotal role in giving particles their mass. The second one is event reconstruction. Detectors like ATLAS and CMS play a crucial role in capturing data from high energy collision. For example, they use calorimeters, magnetic field, and also precision trackers. The third one is jet substructure analysis. When the Higgs boson decays into quarks, these quarks produce jets of particle. This jet substructure analysis will use advanced algorithm to analyze the jet pattern. Next, we also use trigger system to detect Higgs boson. Trigger systems are real-time decision-making tools that rapidly filter out unimportant events while preserving potential Higgs-related events. This is because in the LHC, billions of collisions occur every second. This will generate an overwhelming amount of data. Trigger system is important is because without the trigger, the volume of data would be unmanageable. And triggers prioritize event with decay pattern which consistent with the Higgs boson. This will ensuring variable data is not lost. Lastly, we can use Higgs boson decay signature. This is because Higgs boson decays almost spontaneously. So that is why we cannot observe directly. Instead, the presence of Higgs boson can be looked through its decay product. So there are a few examples of decay modes, which is 2 photon. These decay modes produce a clean and easily detachable signature in the detectors, making it primary focus for physicists. Next, there is also 2 Z boson. This boson further decay into leptons, which can be traced in the detector. The last example of decay modes is bottom quarks. Quarks decays are more challenging to detect due to their similarity to the background noise, but they provide valuable information about the Higgs properties.
Application of Higgs boson. The discovery of Higgs boson has been beneficial to the engineering field. It has been applied in different industries like in manufacturing, transportation, heat transfer, in defense, and lastly, miscellaneous. In manufacturing, metal with lower mass was produced, and lower heat capacity will allow the metal to work in lower temperature. Alloys formed will be homogeneous and have better quality, as well as the reduction of the wastage and oxidation. Other than that, the mass of the metal can be increased during the high mass compaction of materials by increasing the effect of the Higgs field. This happened when the material was densely packed, making it stronger and more durable materials. Lastly, the force required for machining will be reduced when the mass of the material is reduced, enabling us to achieve greater tolerance with lower power tools. Application in Higgs boson in transportation will allow us to use small engines lorries and allowing the transport easier by reducing the mass of materials as it was transported in big loads, which means we can use a smaller lorries to transport materials in the bigger loads to make it faster and easier. Secondly, heavy construction equipment can be transported easier and faster to the remote location as the mass payload reduced. This can take a faster time to the remote location, which is location that is far away from city and can be done all the job in less time. And lastly, the effect of the gravity can be reduced as the mass of the materials will reduce, thus making the launch of satellites and research equipment into the orbit possible. As the weight of the satellites and research equipment has decreased, the effect of the gravity will decrease as well, making sending the satellites and research equipment easier to the orbit. In heat transfer, the heat capacity of a sink can be increased as they have higher mass, allowing it to withstand the heat and not easily break down. For example, when we pour hot boiling water into it, so it can last longer. Other than that, coolant could be made more efficient by increasing its mass when it passes the engine and reducing it when it's in the radiator to allow it dissipate the heat faster. Lastly, CPUs could handle more heat as the mass increased, allowing longer periods of time, greater efficiency, and faster operation as we can get a better devices now. As the application of Higgs boson also beneficial in defense. By increasing the mass of armor plates, the momentum experienced by it will be absorbed more and can be transferred faster when the mass is reduced. Second, for that, high-speed projectiles are produced due to the lower mass, making the penetrative power to cut through the armor plates. Lastly, explosive payloads can be transferred faster and use less energy when the mass is reduced. For the miscellaneous part of the application, low mass vapor allows the process to be faster during the vapor deposition in lower temperature. Coating with high durability can be created by using high mass fill to harden the vapor. By making the possibility of smaller circuits and smaller devices by using low mass field. This help by making the mobile devices. Gases and volatile substances can be handled and transported easily by increasing their mass and limiting their movement. So there will be less mass when these substances will transport from one place to another place.